Hello, welcome to Chapter 6 Problems from the textbook. Okay, again, let me say outlines, notes on any of the videos will be for extra credit. Have a paper and pencil handy so that you can predict the answers. What produces acceleration? What produces acceleration? Well, acceleration is produced by a force, an unbalanced force. If you have unbalanced force, then you'll accelerate. If there is no unbalanced force, in other words, if the net force is zero, then you have no acceleration. You have constant velocity. So the answer would be net force. In Chapter 4, we defined acceleration as the time rate of change of velocity. What other equations for acceleration is given in this chapter? A equals force over mass. Is acceleration directly proportional to mass, or is it inversely proportional to mass? Is acceleration directly proportional to mass or inversely proportional to mass? Well, it's a product, so it's a product constant, so it would be inversely proportional to mass. Product constants MA equals F, where F would be constant. A product constant is an inversely proportional relationship, and vice versa. Not vice versa. A quotient constant would be proportional or direct. If two quantities are inversely proportional to each other, does that mean as one increases, the other increases? No, just the opposite. As one increases, the other decreases, and vice versa. If the net force acting on a sliding block is tripled, what happens to the acceleration? Well, force and acceleration are direct, so it would be tripled. Acceleration also triples because it's a direct relationship between acceleration and force, and mass and force as well. Next, it would be the next slide. So let's wait for number 6, but understand that force and acceleration and force and mass are both direct. If the mass of a sliding block is tripled at the same time the net force on it is tripled, how does the resulting acceleration compare with the original acceleration? So if the mass of the sliding block is tripled at the same time the net force on it is tripled. Okay, triple the force on 3 times the mass in no change in acceleration, because it's going to cancel out, because force and mass are proportional. So if you triple one and on 3 times the mass, so you triple the force and triple the mass, this results in no change of acceleration because they're proportional. Motion is affected by solid objects in contact. In what other ways, situations, does friction affect motion? In fluids, through a liquid or air. Suppose you exert a horizontal push on a crate that rests on a level floor and it doesn't move. How much friction acts compared with your push? Same magnitude as your push, oppositely directed, producing a 0 net force. And number 9, how great is the air resistance that acts on a 10 Newton sack that falls in air at constant velocity? 10 newtons. Then the net force equals 0. The net force equals 0. So there would be, they would cancel out. Okay, distinguish between force and pressure. Force is per unit area. Force and pressure are proportional. They are direct. However, force is force, and pressure is force per unit area. When do you produce more pressure on the ground? Standing or lying down? Well, you would be presenting a larger surface area so that you would when you produce more pressure on the ground, standing or lying down, for more pressure when you're standing due to less area of contact. So you're presenting less area, so force divided by less area would be more pressure. Okay, what is meant by what is meant by free fall? I guess I didn't do 12. So what is meant What is meant by free fall? Free fall occurs when only the force of gravity acts, no air resistance. Different meanings to a skydiver, where free fall means falling in air before parachute is opened. Free fall means there's no support force, there's no normal force when you're free falling. So there's only weight. You still have the weight, you still have gravity, but there's no support force. Okay. For some reason, this is a longer one. Okay. Oh, here's number 12. Why is it important that many nails are in the boards in the figure 6.7? Because you have greater area and the pressure is reduced because force per unit area. The more nails you have, the more the pressure is reduced. So if you only had one nail, it would go right through them easily. So if you have many nails, more surface area of nails against his body, so less pressure when hammer hits. Okay. And then the next one. Okay, here we go. That was pretty easy, actually. The ratio circumference to diameter for all circles is pi. What is the ratio of force per mass for all freely falling bodies, regardless of where you are, on Earth, on the Moon, on Mars, whatever the case may be? It is G. It is the acceleration due to gravity, the acceleration of free fall. Why doesn't a heavy object accelerate more than a light object when both are freely falling? Why? Because, well, the mass and the force are proportional to one another. There's a direct relationship between the two. So you would say greater mass means proportionally greater weight, and hence proportionally more force. The ratio F equals F divided by M is unchanged with equal accelerations in free fall. In other words, if you're on the same planet or at the same elevation on the same planet, the ratio of F to M will be the same regardless. Increases. Oh, sorry. The question is, does air resistance on a falling object increase or does it decrease with increasing speed? It increases. The faster it goes, the more molecules it hits, the greater the pressure. The greater the pressure, the greater the force. The greater the force, the greater the upward force, the greater the air resistance. If two objects of the same size fall through air at different speeds, which encounters the greater air resistance? The faster falling object. Because the faster you're going, the more molecules you're going to hit, the greater the pressure, the greater the force per unit area. So the greater the force, the greater the speed, the greater the pressure, etc. What is the acceleration of a falling object that has reached its terminal velocity? What is the acceleration of a falling object that has reached its terminal velocity? Well, terminal velocity, velocity, constant velocity. So the acceleration would be 0, 0, 0, 0. What besides speed affects the air resistance on a sky diver? What besides speed affects the air resistance on a skydiver? So it would be the surface area. In other words, are they lying flat? Are they pretending they're a bird? Are they going feet first and going straight down? So surface area, depending on the body orientation. More area presented to the air, the more resistance, the greater the sooner they're going to reach terminal velocity, the sooner. And why is that? So terminal velocity is a tricky nut to crack in this unit. How much air resistance acts on a falling 100 Newton box of nails when it reaches terminal velocity? 100 Newtons. Because the downward force has to equal the upward force. So there's no unbalanced force. That's why. So here we go. We're going to spend some time on these next few. It says each diagram shows a ball traveling from left to right. Kind of looks like eggs, but they're balls. Think round, just the orientation. The position of the ball each second is indicated by the second. Rank the net forces from greatest to least required to produce the motion indicated in each diagram, A, B, C, D. Right is positive and left is negative. Right is positive and left is negative. All right, so going to the right is positive. Okay, so it would be D, B, A, C. So D, B, A, C. Each diagram shows the ball traveling from left to right. So all the balls are traveling from left to right. The position of each ball, each second, is indicated by the second. Rank the net forces from greatest to least required to produce the motion indicated in each diagram. Right is positive, left is negative. Okay. Right is positive, left is negative. Let's look at this again. See, it's confusing when you first look at it because of the colored balls, but each ball is a different frame. So it's all one ball, and the ball on the D is going the fastest, so that's going to have the largest net force, and then it would be B, then A, then C. So it'd go D, B, A, C. Okay, boxes of various masses are on a friction-free level table. Rank each of the following from greatest to least. The net forces on the boxes. All right, so the net force in A would be 5 to the right, then 5 to the right, then C would be 5 to the right, and D would be 10 to the right. So it would be D would be the largest, and then A, B, and C are equal. And then the accelerations of the boxes, it would be the same thing. It would be D, and then A, B, and C all to the right would be equal. Okay, so A, B, and D. A, B, and C would be equal. They'd all have the same net force. Oh, sorry, no, that would not be correct. Because why wouldn't that be correct? If you had 5 kilograms, 10 kilograms, 5 kilograms, 20 kilograms. So it would be different than that. So let's take this again and examine it more closely. So what do you think? Well, A would be 5 over 5 is 1, force over mass. B would be 5 over 10 is 0.5. C would be 5 over 5 is 1. And D would be 10 over 20 is 0.5. So it would be A equals C and B equals D in that order. Okay, each block on a friction-free lab bench is connected by string and pulled by a second falling block. Rank each of the following from greatest to least. The acceleration of the two block systems, and B, the tension in the strings. Okay, this is a little confusing. I'll go over this in class. Remind me. The acceleration of the two block system, let's see. What would be greater? It says each block on a friction-free table bench, friction-free lab bench is connected by a string and pulled by a second falling block. Rank each of the following from greatest to least. The acceleration of the two block system. In other words, the entire block system is moving. The entire block system is moving. So, and then you want to look at the tension in the string. But remember, the tension is, let's say you hold a brick on a string. Okay, you feel the tension in the string? You feel it? Okay, now, accelerate the brick downward. Isn't the tension a little less? Okay, but, so that's kind of the answer to B. However, what would the acceleration of the two block system be? Which one would, it says, rank each of the following from greatest to least. So which would have the greatest acceleration? The greatest acceleration. Which one would accelerate? Now remember, B is a 4 kilogram system, C is a 6 kilogram system, and A is a 4 kilogram system. But you see intuitively that it would be B, then C, and then A. A would actually be accelerating the least. A would be accelerating the least. And what about the tensions in the string? So do you see how C would be the greatest tension? Okay, now remember, you have 6 kilograms there, and then it would be A and C are actually equal. Okay, and we'll look over that in class. All of the aluminum blocks have the same mass and are gently lowered onto a gelatin surface, which easily supports them. All have the same bottom surfaces. Rank them by how much they dent into the surface from greatest to least. So what has the greater pressure? They're all the same. What has the greater pressure? What is the greater pressure? I want you to try to think about that. So wouldn't C have the greater pressure? And then it looks like then D, and then B, and then A. So C would be the skinniest, then D, then B would be next, and then A. So it would go C, D, B, A would be the answer to that. Because they all have the same force. They're all the same weight. Yeah, they're all the same weight. And it's the surface area. So the smaller the area, the larger the pressure. Okay, so smaller the area, the larger the pressure. So area and pressure are inversely proportional to one another. Okay, number 25. Calculate the acceleration of a 40 kilogram crate of softball gear when pulled sideways with a net force of 200 newtons. So 200 newtons equals 40A. So wouldn't it be 200 divided by 40? Wouldn't it be the acceleration? Wouldn't it be? It's not falling, it's going sideways. So A equals 5. Hopefully that's what you got. All right, A equals 5. Hopefully that's what you got. The next one is going to be, this is a little too long, I think, for this. How many seconds is this? Well, anyway. So it's simply going to be force over mass. Force over mass. And that equals 5. Okay, calculate the acceleration of a 2,000 kilogram single engine airplane as it begins its takeoff with an engine thrust of 500 newtons. So it would be 500 divided by 2,000, and that'll be 500 divided by 2,000, which would be 0.25. Would have that acceleration of 0.25 meters per second squared. So you see why you might need a long runway to get it up to speed. Calculate the acceleration of a 3,000 kilogram jumbo jet just before takeoff when the thrust for each of its 4 engines is 30,000 newtons. It'll be 0.4 meters per second squared. 0.4 meters per second squared. Again, you see why you might need a long runway, because it's such a heavy plane, such a large mass plane. Calculate the acceleration if you push with a 20 Newton horizontal force against a 2 kilogram block on a horizontal friction-free air table. So it's 20 newtons divided by 2 kilograms is 10 meters per second squared. 10 meters per second squared. 20 divided by 2 kilograms. 20 newtons divided by 2 kilograms. Calculate the horizontal force that must be applied to a 1 kilogram puck to make it accelerate on a horizontal friction-free air table with the same acceleration it would have if it were dropped and fell freely. It would be 10 newtons because the acceleration is 10, so it would be 10 newtons. Calculate the horizontal force that must be applied to produce an acceleration of 1.8 grams, 1.8 g for a 1.2 kilogram puck on a horizontal friction-free air table. So it'll be 1.8 times 10, which would be 1.8 g, times the 1.2 is 21.6 newtons. Next, if you push horizontally on your book with a force of 1 newton, to make the book slide at a constant velocity, how much is the force of friction on the book? 1 Newton in the opposite direction to the push. Terry says that if an object has no acceleration, then no forces are exerted on it. Sherry doesn't agree, but can't provide an explanation. They both look at you. What do you say? Well, Terry should have said that no net forces are exerted on it. Say that Terry would be correct if she said net force. When a car is moving in reverse, backing from a driveway, the driver applies the brakes. In what direction is the car's acceleration? It would be decelerating if you apply the brakes, so it would be negative. When the car moves backwards, acceleration is forwards in the direction of the net force on it, decreasing the speed of the car. Ask me in class and I can show you on the board. That really needs a better free body diagram to make it a little clearer. All right, the auto, there's no sketch. The auto is in the sketch moves forward as the brakes are applied. A bystander says that during the interval of braking, the auto's velocity and acceleration are in opposite directions. Do you agree or do you disagree? Well, it's going forward, that's positive, but you're decelerating, and that's negative. You agree, the acceleration is opposite the velocity. Even though you're not backing up or going in the reverse direction, you're decelerating. So he is decelerating. That's what the difference is. What is the difference between saying that one quantity is proportional to another and saying that it is equal to another? Force is proportional to mass, but 2 is equal to 2, or 2 is equal to 4 over 2. Proportional. A change in one quantity implies corresponding change in another, identical when one quantity is equal to another. What is the acceleration of a rock at the top of its trajectory when thrown straight up? Let's see here. Is it 0? What is G at the top of its trajectory? It's always G. It is always G. When blocking in football, why does a defending lineman often attempt to get his body under that of his opponent and push upward? What effect does this have on the friction force between the opposing lineman's feet and the ground? If you get the player off the ground, then they can't use any friction to propel themselves forward. So you're reducing the friction really to 0. You can't reduce ground contact and friction between the opponent's feet and the ground. An aircraft gains speed during takeoff due to the constant thrust of its engines. When is the acceleration during takeoff greatest? At the beginning of the run along the runway or just before the airplane takes off? The acceleration is greatest at the beginning because you have very little air resistance. You have very little drag, so it's going to be greater at the beginning of the takeoff when air drag is least. Okay, next. A rocket becomes progressively easier to accelerate as it travels through outer space. Why is this so? Because you're reducing the mass of the engine fuel. Reduce mass, increase acceleration. Reduce mass, increase acceleration. A common saying goes, if it's not the fall that hurts you, it's the sudden stop. Translate this into Newton's laws of motion. Well, if you have a large acceleration or deceleration, you're going to have a large force, because acceleration and force are direct. They're proportional to one another. So just as mass and acceleration are indirect, acceleration and force are directly proportional. So don't be fooled by a sudden stop. Because you're stopping, you're decelerating, which means you still have a large acceleration. So the force would be great as a result of that. So by A equals F over M, a sudden stop means a great A, which means a great F for a given mass. Okay. On which of these hills does the ball roll down with increasing speed and decreasing acceleration along the path? Use this example if you wish to explain to someone the difference between speed and acceleration. On which of these hills does the ball roll down with increasing speed and decreasing acceleration? Well, the acceleration is going to slow down in the middle one, so it's on the middle hill where the slope becomes less towards the bottom. So even that you'll still be increasing the speed. Why does a sharp knife cut better than a dull knife? Smaller cutting area produces greater pressure for a given source, less surface area. When Helen lifts 1 foot and remains standing on a bathroom scale, pressure on the scale is doubled. Does the weight reading change? Does the weight reading change? No. The scale reads force, not pressure. Aristotle claimed the speed of a falling object depends on its weight. We now know that objects in free fall, whatever their weights, gain speed at the same rate. Why does weight not affect acceleration? By A equals F over M, F equals mg. In free fall, A equals mg over M equals g. Mass cancels out. So mathematically, you can see how that's actually quite true. After learning why objects of different mass have the same acceleration free fall, Erik wonders if objects tied to equal lengths of string would swing together in unison. Lisa wonders if objects of different masses would slide at equal speeds down a friction-free inclined plane. What is your thinking on these hypotheses? What is your understanding? What's your thinking on these hypotheses? Both are correct. The effects of force inertia are not confined to free fall at all. They are not confined to free fall. In a vacuum, a coin and feather fall side by side. Would it be correct to say that in a vacuum, equal forces of gravity act on both the coin and the feather? Act on both the coin and the feather? Absolutely, positively not. The reason is that ratios of weight over mass are equal. As the skydiver falls faster and faster through the air before reaching terminal speed, does the net force on her or him increase, decrease, or remain unchanged? Does her acceleration increase, decrease, or remain unchanged? Defend your answers. Well, when you're falling through the air, skydiving, when you first jump out, you're accelerating at 10 meters per second squared. But then the more air you hit, the less you're going to accelerate. And soon you're going to stop accelerating and you're going to hit terminal velocity. So as soon as you jump out the plane, you're accelerating the most, and then you decelerate. So it's going to be decreases, resisted by air drag. After she jumps, the skydiver reaches terminal speed after 10 seconds. Does she gain more speed during the first second of fall or the 9th second of fall? Compared with the first second of fall, does she fall a greater or lesser distance during the 9th second of fall? Can you think of a reason why the acceleration on an object thrown downward through the air would actually be less than 10 meters per second squared? Okay, so I read both questions, so let's take 48 first. Maximum gain in speed occurs during the first second of fall. Since her speed increases, she will be falling faster during the last second of the fall and therefore cover the greatest distance during this time. But the increase of speed will be less. The rate of increase will be less because they'll be reaching terminal velocity. And then number 49 is, with air drag, acceleration is actually less for higher speeds. How does the weight of a falling body compare with the air resistance it encounters just before it reaches terminal velocity, just after it reaches terminal velocity? Why does a cat that falls from a 50-story building hit the safety net with no more speed than it fell from the 20th story? Because it reaches terminal velocity at about the 20th story, which is a little bit weird of a problem, but that's actually quite true. Anyway, number 50, just before terminal velocity, weight is slightly greater than air drag. After reaching terminal velocity, weight is equal and opposite to air drag. So it would be, at, terminal velocity is that they're equal, so that they're, there's not a problem. There's not a problem with that. So when they reach it, when they reach terminal velocity, there is no, they're equal. The air drag's equal. So here's Mr. Cat falling from a 50-story building, and he's going to be safe. He's going to be fine. Once anything reaches terminal velocity, no increase in speed occurs. This occurs for a cat at about the 20th floor. So I'm not quite sure who measured that, but a little weird. But anyway, a regular tennis ball and another filled with sand are dropped at the same time from the top of a high building. Your friend says that even though air resistance is present, both balls should hit the ground at the same time because they are the same size and pass through the same amount of air. What do you say? What do you say? Very interesting. Well, the heavier ball will reach terminal velocity later because it has a greater weight. So the heavier ball. If you drop an object, its acceleration towards the ground is 10 meters per second squared. If you throw it downward instead, will its acceleration after throwing be greater than 10 meters per second squared? Why or why not? Ignore air resistance. If you're on the same planet, well, it's always going to be 10 meters per second squared. If it has initial velocity, v naught t plus 1/2 gt squared, but it's always going to, the speed is different, but the initial speed is different, but the acceleration is still 10 meters per second squared. It still gains 10 meters per second squared for each second. It's the acceleration is that. So anyway, Suzy Skydiver, who has a mass of m, steps from a basket on a high-flying balloon of mass m and does a skydive. What is the net force on Suzy at the moment she steps from the basket? What is the net force on her when air resistance builds up to equal half her weight? What is the net force on her when she reaches terminal velocity v? What is the net force on her after she opens her parachute and reaches a new terminal speed, 1/10 v? So she's going to slow down, obviously. So what's the story? Well, as soon as she jumps out of the plane, the basket, the balloon, her net force is equal to her weight because there's nothing contrary to that. Just a split second after. That's A. What is the net force on her when air resistance builds up to equal half her weight? Well, it would be, the net force would be half her weight. And then what is the net force on her when she reaches terminal velocity? 0. And what is the net force on her when she opens, and she's reaching new terminal velocity? Her net force would be 0 as well. So it would be her weight, half her weight, 0 and 0. That should be it, unless I have no idea what I'm doing. So, good problem though, very good problem. So with no air drag yet, F net equals her weight. As we proceed here, let's go more quickly through this. Let me change the timings on this. The next one would be half her weight, as I said there, and then 0 net force, and then 0 net force. Okay, a net force of 2 kilogram cart A net force on a 2 kilogram cart accelerates the cart to 3 meters per second. How much acceleration will the same net force produce on a 4 kilogram cart? Well, let's say it's 2 times 3 is 6, and then 6 equals 4a. A would be 1.5, so you'd be half again. So how much acceleration will the same net force produce on a 4 kilogram cart? It would be 1.5 meters per second squared. Because remember, they're saying that, you know, it's going to be the same force, and we know that force equals ma, so it'll be 2 times 3 is 6, so 6 equals 4a, so 6 divided by 4 is 1.5, so it would be 1.5 would be the answer there. Okay, and that's absolutely the case. Okay, so next, 57, we're almost finished. A net force of 10 newtons is exerted by Irene on a 6.7 kilogram cart for 3 seconds. Show that the cart will have an acceleration of 1.5. Well, it would be 10 divided by 6.7, which is 1.5. So 1.5 times 6.7 is 10. So that's pretty straightforward. And that's exactly the case. Remember that acceleration is change in velocity over time. So Toby Too Bad has a mass of 100 kilograms, is skateboarding at 9 meters per second when he smacks into a brick wall and comes to a dead stop in 0.2 seconds. Show that his deceleration is 45 meters per second. That's 4.5 times g. Ouch. He starts from rest, and yes, it's going to be 9 is going to be the change in velocity. 9 divided by 0.2 seconds is going to be 45 meters per second squared, and that's going to be from rest. It's going to be from rest. So going to be 45 meters per second squared. A net force of 10 newtons on a box of plastic foam causes it to accelerate 2 meters per second squared. Show that the mass of the box is 5. Well, I hope you can do this by now. 10 divided by 2 is 5. 10 divided by 2 is 5. Okay, moving right along here. We are zipping along. Let's take a break. Austin's truck has a mass of 2,000 kilograms. When traveling at 22 meters per second, it brakes to a stop in 4 seconds. Show that the magnitude of the braking force acting on the truck is 11,000 newtons. Well, it's going to go from 22 to 0, so 22 divided by 4 is going to be 5.5, I guess. So 5.5 times 20, 2,000 is going to be 11,000. So let's check it out. F equals ma, blah blah, change in velocity over time, and that's going to be 11,000. That's absolutely correct. If a loaded truck can accelerate at 1 meter per second squared, it loses its load and has 3/4 of its mass left over. So on a truck, what acceleration can it attain if the same driving force acts on it? So the same driving force is going to act on it. So this is going to be a little bit more complicated, but we're going to go through this very quickly. All right. So F1 is before, F2 is after. So it's going to be M1 A1 equals M2 A2. Now remember, A2 is going to be 0.75, 0.75 of M1. Okay, so then that's going to, the M's are going to cancel. Actually, M1's are going to cancel, and you're left with A1 equals 0.75 A2, and then you're going to plug in for A1, and then you're going to divide through, and you're going to get 1.33 is going to be A2. Okay, next. An occupant of a car can survive a crash if deceleration occurs if deceleration during the crash occurs is less than 30 g. It's kind of a lot. That's amazing. calculate the force of on a 7 kilogram person decelerating at this point. So it'll be 30 G. So it'll be 30 times 10 times 70. So that's pretty amazing. So it'll be 21,000 newtons. That's amazing. I weigh 1,000 newtons. Man, I'll tell you, that would be very painful indeed. Okay, what is the pressure on a table in a 20 Newton book with a 0.05 meters squared cover, lies flat on it? What is the pressure when the book stands on its end? The area is 0.01. So it's going to be 20 divided by 0.05, and that'll be 400 newtons per meter squared, which are pascals, and then 20 divided by 0.01, which would be 2,000 pascals. So it'll be 400 and then 2,000, respectively, pascals. And that's the case. Pretty straightforward. P equals F over A. No problema. The next one is pretty straightforward. So let's go to the next one. And it says, right now, a falling 50 kilogram parachutist experiences upward acceleration of negative 6.2 meters per second squared when she opens her parachute. Show that the drag force is negative 810 newtons when this occurs. So down is positive, up is negative, even though the book says the opposite. I don't know, but whatever. So it's very easy to show this. Very easy to show this because don't forget to add the negative 10. Negative 10 upward as well, plus the 6.2. So that's going to be 50 times 16.2, which is 810. A 10 kilogram mass on a horizontal friction-free air track is accelerated by a string attached to another 10 kilogram mass hanging vertically from a pulley as shown. What is the force due to gravity in newtons on the hanging 10 kilogram mass? What is the acceleration of the system of both masses together? All right, so what is the force due to gravity in newtons on the, so the 10 kilogram mass that's hanging off the table is going to be 100 newtons, but the mass of the system is going to be 20 kilograms. The mass of the system is 20 kilograms, so it'll be 100 divided by 20, which will be 5. That will be the acceleration once the system gets going, and there's no friction, obviously. So there's the weight of the block hanging off the table. So its acceleration will be 5. And there it is. So 100 divided by 20 is 5. Don't forget, it's the whole thing is accelerating, the whole system. And it's the 100 Newton mass that's doing the accelerating. Suppose the mass described in problem 65 are 1 kilogram and 100 kilogram respectively. Compare the accelerations when they are interchanged. That is for the case where the 1 kilogram mass dangles over the pulley, and then for the case where the 100 kilogram mass dangles over the pulley. What does this indicate about the maximum acceleration of such a system of masses? Okay, so it would be 100, 1,000. The first one, where it's like this. The first one is, it would be 100, 1,000 is going to be the force divided by 101, and then it would be 10 divided by 101. Okay, so that's the first one, where the 1 kilogram mass is hanging over the end. It would be 10 over 101, and then it will be 101 or 100 over 101. So that's the first one. That's where the 1 kilogram one is hanging off the side. And then the next one is going to be where the 100 kilogram one is hanging off the side. And they're writing it in terms of the ratio of masses. That's how they're writing it. So, you know, you're going to have very little acceleration when the 1 kilogram mass is hanging off the side. So it's going to be 0.99. So it'll be, you know, just a little bit less than G, but G will be the, you know, the maximum is going to be G, the absolute maximum. So if it's frictionless, so it'll be less than that, however. Okay, now next. Skelly the skater is propelled by rocket. Skelly and the rocket together have a mass of 25 kilograms. The thrusting force is 100 newtons and the friction is 20 newtons. What is Skelly's acceleration? How far does he go in 5 seconds if he starts from rest? Okay, let's see if we can do this one. All right. So, what is going to be the answer? Let's see. Skelly is, let's see, 25 kilograms. The thrusting force is 100 newtons and the friction is 20. So it's going to be, the acceleration is going to be 3.2 meters per second squared. And the distance is going to be 1/2, because it's going to go from rest, 1/2 times 3.2 times 5 seconds squared, which is 40 meters. Okay, so that's 40 meters. And that brings us to an end. And Skelly's acceleration will be 3.2 meters per second squared, and the distance she travels will be 40 meters. Okay. Study for your test and your quiz, and we'll talk later. Bye.